This is Unit 8, and we are looking at our fifth and final type of chemical reaction. This chemical reaction is a double replacement reaction. And what happens in this reaction is that two ionic compounds react. What we get are two different compounds being produced. So the reactants are two ionic compounds. The products are two different compounds. Usually this happens between two ionic compounds that are dissolved in water, which, as we learned earlier, these are aqueous solutions. Really two words that mean the same thing. In this reaction, the compounds exchange ions. A double replacement reaction follows this general equation. So A and B represent cations. X and Y represent anions. And so what's happening is you're basically switching. A and Y will become a compound, and B and X will become a compound. There's only one way that you could swap these, and this is how they're doing it. So when this happens, the thing to keep in mind, they're ionic compounds. So when we figure out what the products will be, we have to consider the charges. So let's look at two examples here. So we have this solid ionic compound, and we are going to add it to this aqueous HCl. And when we add the solid to this aqueous solution, they're both going to be in the solution at that point. So we need to first off predict the products that we're going to have. Here's something that might be helpful. And let me pick a different color. Something that may be helpful is to figure out the charges of all of these elements before we even start writing things over here. It can make it a little bit easier. Now, I'm not going to be writing the charges like this as if they were actually, required parts of the compound, because we don't put the charges there. But I'm going to write them maybe just a little bit above. So sulfur, I looked at the periodic table, it's in group 16, and I know that everything in group 16 has a -2 charge. And I have one sulfur and one of these irons, and for this compound to be neutral, the iron has to be 2+. I'm working backwards. For HCl, I know that hydrogen is in group 1, everything in group 1 has a +1 charge, and I know that Cl is a halogen, every halogen has a -1 charge. So when I start putting things together in the products, it's going to make it a little bit easier now that I know what these charges are. Here's how they're going to pair up. Hydrogen and sulfur are going to pair up. Iron and chloride are going to pair up, just like they did here. And it doesn't really matter which one you put first. I'm going to go with the hydrogen and the sulfur. So here's the hydrogen and the sulfur, and so I switch them H2S. I'm going to leave some space here for the state. The second thing is this iron 2 chloride. So we have iron 2 and chloride, FeCl2. So what I'm going to do for now, I'll put the states in. We can talk about these later. H2S, going to be a gas, and the iron chloride's aqueous. The last step here, this thing is not balanced. And we want to make sure that when we have a chemical equation written, that we've balanced it. And so for this one, what I'm going to do is go ahead and write all these out. 1, 1, 1, 1. 2 hydrogens, 2 chlorines. And so it's the hydrogens and the chlorines that are unbalanced. And we want these to be 2s, which means we're going to add a coefficient of 2 right here. And when we double check it, 2 hydrogens, 2 chlorines, 1 iron, 1 sulfur, everything else checks out. All right, I'm going to skip a little bit, leave some space here, and this next one, Li2SO4 plus BaCl2. 2 aqueous compounds reacting. Follows the same basic pattern. Here's how they're going to pair up: lithium and chlorine, barium, and this SO4 is one piece. Remember, it's a polyatomic ion. So when we talk about polyatomic ions, they are at the end of the ions and ionic bonds unit. And there's a paper, a handout that I gave you that you can take a look at. Like we did in the last one, I'm going to go ahead and find the charges for everything. Let me get this out of the way. That too. So the charges for these: lithium, alkali metal, +1. Barium, alkaline earth metal, +2. Chlorine, halogen, -1. The only thing we really don't know is this SO4. But if you look at it, there's only one of these SO4s, and the charge of this is 1. So if you were basically uncrossing the charges, this 1 would make sense, which means that this 2 would end up here. SO4, not 2 plus, 2 minus. There you go. And so it's possible, even if you don't know the charge of something, you can figure it out based on whatever it's paired up with. And so in the products, we're looking at lithium chloride, and these both have charges of 1, plus 1, minus 1. This ends up being aqueous. And the other one is barium with this sulfate, and they both have charges of 2, plus 2 and minus 2, and those will cancel. BaSO4. And we'll talk about this in a later video. This one ends up being a solid, and I'll explain why later. The last thing is just to make sure that it is balanced, and right now it's not. See here I have 2 lithiums and 2 chlorines. Here there's only 1. Now it has 2, 1 barium, 1 SO4, and now it's balanced. So we're going to come back to this page a little bit later after we've talked about a couple more topics and fill in some more things in the middle. This next section, starting on page 9, reactions in aqueous solution. And really what we're doing in this section is talking more about double replacement reactions. So we've got 2 ionic compounds dissolved in water. And what happens when we dissolved it, it dissociates or separates into its positive and negative ions. Look, dissolves, dissociates. Very, very similar words here. So here's what's happening. As an example, sodium chloride, and we're going to put it in water, and it breaks into its ions like this. This is what it means when it dissociates. Now, to keep things short, we typically would just write it like this. And we know that we've dissolved in water, and we know that they've split apart. This just saves us a little bit of space, a little bit of writing. Either one of these would be acceptable. When 2 aqueous compounds are combined, the ions are able to react. When they're solids, they don't really have the capability to react much, but once they're dissolved in water, the reactions can go pretty fast. So the cation of one compound may react with the anion of the other compound. Basically what's happening here, ions are rearranged in this type of reaction. When a double replacement reaction occurs, one of 3 products forms. It's either a gas, a precipitate, or water. We've talked about these before. Production of a gas, we can observe it in an aqueous solution. It's bubbles. We can see a precipitate. It's a solid product. It's no longer going to be dissolved. At first, it may just look cloudy in the solution, but it's going to pretty quickly, everything sinks to the bottom of the container. The third thing, water, which we didn't talk about earlier in observing chemical reactions. Because we have a problem here. We have two compounds dissolved in water, and when they react, they create more water. We're not going to be able to see it. We're not going to be able to measure it. So observing the production of water is difficult. Basically, the way it's going to happen, it's predicted on paper. So we know that water was produced on paper, which tells us that we know it happened in the real world. We just couldn't see it because we were looking for a little bit of water when there was a lot of water everywhere. So what happens when none of these three products are formed? If nothing formed when two aqueous solutions are combined, possibly both of the products are soluble in water. And when you mix two ionic compounds that are dissolved in water, but they don't react or form a product because everything is soluble, what did we actually do? And this is what I would say. Not much. We mixed two chemicals in the same container. So we can predict the products of an aqueous reaction. We did it just a little bit ago on the previous page. The cation of the first reactant combines with the anion of the second reactant, and same with the other two. When writing the chemical equation, we need to write the appropriate chemical formula of each compound. Remember our switching the charges, that's what we're going to be doing. So we can identify if a reaction occurred by looking at the products. If water was a predicted product, a reaction occurred. If a compound forms and you know it's a gas, like for instance hydrogen or oxygen gas, a reaction occurred. When we predict that ionic compounds form, we have to check if the products are soluble in water. A compound that is insoluble forms a precipitate. A reaction has occurred. Remember, a precipitate is a solid. When both compounds and the products are aqueous, remember it means we mix two chemicals in the same container. There was no reaction. We just mixed two things. And same as before with the single replacements, we're not going to rewrite all of our chemicals. We're just going to write no reaction, NR. So in example 8, there's a lot of space here. What we're going to do is, given two aqueous ionic compounds, we're going to predict the products. We're going to predict their solubility to see if something actually happened or if we just mixed two things in the same container. So the first one, barium chloride plus magnesium sulfate First thing is predict the products. This is where it's helpful to know their charges. So this Ba is in group 2, Cl is in group 17, magnesium's in group 2, and there's one magnesium for every one of these SO4s. Means the SO4 has a charge of -2. So here's how they pair up. Cation of one with anion of the other. A charge of +2 for the barium, a charge of -2 for the sulfate, and so we end up with BaSO4. So I want to know what state is this going to be in. I have to check its solubility. Is this going to be aqueous or is it going to be solid? To figure this out, I have to flip to page 11. Page 11 has the activity series, but it also has this box, this table that says solubility rules for ionic compounds. And so we're looking through this first column. It says compound contains. And we're looking at each of these. We're looking for sulfates, SO4 2-. So then I look over one row, and it says it's going to be soluble. So we should be okay here. But then we always have to check the exceptions. Barium is an exception. So they're usually soluble, but when it's barium, it's insoluble, which means solid. It's going to be a solid. It's going to form our precipitate solid. The other compound will form between magnesium and chloride. And so you'll want to know its formula, switching the charges. MgCl2. So I'm going to write my parentheses, and then I'm going to go check that chart. So compound contains, let's see, no, chlorides, Cl-. They are going to be soluble, which means aqueous. But let's check the exceptions. We're looking for magnesium. I don't see anything here. So we're going to end up with an aqueous compound. The last thing to do is to see if it's balanced. And we have one barium, two chlorides, one magnesium, one SO4, one SO4. And so this one is balanced. In the next one, we have potassium chloride and sodium nitrate, and these are going to react. And so we're going to end up with two different ionic compounds. That would be potassium with nitrate and sodium with chloride. So before we write anything down, you could write it down if you want, but let's check to see, are these things going to be soluble? So let's look at sodium chloride. And here we are with chloride salts. We said that they were soluble, or in other words, aqueous. And sodium is not listed in the exceptions. And so sodium chloride would be aqueous. Let's check the other one too, potassium nitrate. So we look at our page here. Here's nitrates. It says they are soluble, which means aqueous. Check the exceptions. There are no exceptions. Nitrates are always soluble, no matter what. It could have uranium with nitrate. It's going to be soluble. And so both of our products here are aqueous. And so rather than writing out sodium chloride aqueous, potassium nitrate aqueous, no reaction.